Welcome everyone to the spring semester seminars. So this semester we decided to have a few more seminars than usual, and the reason is that it was pointed out that it's a very big group now, and we have a lot of papers coming out all the time, and we never hear about what each other is working on. So we are having external seminars, but also a bunch of 8 or 9 internal seminars. So that would partially replace some of the external speakers and partially take over the journal club spot that wasn't really working out anyway. Okay, so for the first seminar, we're very happy to have our own Guanda that will tell us about a new interesting paper with Jeff and Sean. Take it away.
Okay, so hello everyone. I don't think I need any self-introduction, so let's just get started. Okay, so and also I think a lot of you have heard at least part of the story, so maybe I will just skip the broad introduction or motivation part. Let's just directly get into the question. So the question we want to answer basically is how to when they find the generalized entropy or try to reproduce the QIS prescription, you always say that I suppress the fluctuation of the gravitational field versus the metrics themselves, and talk more about the matter entropy and the interplay between the matter entropy and the area term in generalized entropy. But now I think the question for us is just if we really just want to consider what is the contribution to the generalized entropy from the graviton versus gravitational fluctuations themselves, then what should we do? So this is the question we're trying to answer. And so what could be the puzzle? So some of the puzzles I can think about, maybe I have listed them there. So we know that generalized entropy has this area term, has this bulk entropy term. So first let's look at area. So if you have, say, a gravitational fluctuation just by itself, then it will it's a metric perturbation. So it will perturb the extremal surface away. So when we try to say, okay, I want to evaluate the extremal surface area, is the extremal surface the perturbed one by the perturbation or the unperturbed one? That's, for example, one question. And on the other hand, when we talk about the bulk entropy, well, we tend to treat, or at least that's what we hope, that the gravitons behave not that different from ordinary matter, but we want to make this precise. What's the difference between the bulk entropy contribution from the gravitons compared to the ordinary matter? So that's another part of the question. And for some of you, maybe who have heard about the thing called atomal, because gravity is if you treat it perturbatively, it is a gauge field. So when you deal with the entropy of the gauge field, then there might be some additional contribution living on the entanglement surface that could be important in certain cases. Then in the case we are trying to deal with, to define generalized entropy for gravitons, do we need to think about carefully about actual contribution, or in the end just turn out to be not contribution? So these questions are the questions I would have before we do any specific calculation. And our target would be that to have a definition of generalized entropy, including the graviton contributions, to be first, it's still taking the form of area plus the bulk matter entropy part, and plus some possibly contribution from the degrees of freedom living in the horizon. And to make this formula gauge invariant, because gravity, as I was saying, it is a gauge theory, and hopefully we have a good enough prescription, and if we do ADS-CFT, the bulk definition of the entropy matches the corresponding boundary calculation of the entropy. This will make sure that our prescription is making sense. So this is the target. So up to now, any questions? Okay, so about the results, I would say I would separate the results into two parts. One is more concrete. We can say that we have 99% sure of everything we are seeing here have concrete computational support. But on the other hand, there are some other more interesting results. These more interesting results maybe like you guys would be more interested in and have a lot more discussion on this. So I would first introduce the concrete results. I mean here first, and of course in the later part of the talk, I will also first introduce the more concrete one. And then in the end, I'm going to focus on explaining a little bit of some more exciting, possibly or other results. And then like
a strong word. Results is a strong word.
Okay. Yeah. The last one. Sorry, the last equation here is the proposal. So yeah. Anyways, so this part I think it's still we can call it results. So like yeah. Well, like before the talk, I checked with you. You said you were.
I was about
Okay. I mean, for the concrete ones, we know for sure that in the setup of pure gravity without matter, and we have finite energy in steady state, we don't want the energy to be created large to create a black hole. And in the like very classic RT setup, we know that we can write down like the definition of the area operator, the bulk modular Hamiltonian, and compute the change of expectation value. I mean, with respect to the vacuum, and match that to CFT. And on the other hand, we can also do the relative entropy computation, and the boundary and bulk also match. And if you sum up these two equations together, you get on the left-hand side the like boundary entropy, the boundary vacuum subtracting entropy. On the right-hand side, you have like the bulk vacuum subtracting entropy, and they have a perfect match. So here I should mention that all the results here are valid up to G Newton to the power 0, or say order 1. And my definition of order here is like A over 4G, I would define it to be 1 over G Newton. So this is like the order we are currently working on. And it would be interesting to try to extend to higher orders, but not yet. Questions? Okay. And the more exciting part, or say proposal, would be that we have hopefully a order prescription of define the like gravitational entropy, and this definition involves one important concept. It is called the quantum extremal gauge condition. So we would like to say that if you write down the area operator, write down the like log of the density matrix, and the commutator between this operator and any diffeomorphism acts on the specific state, the state in this quantum extremal gauge, it vanishes. This defines the so-called quantum extremal gauge condition. And for the for the state size satisfying the quantum extremal gauge condition, we use these to define the bulk entropy, and hopefully they can give a all-order prescription go beyond our order G Newton to 0 result. And I would personally want to maybe emphasize a little bit that in our results, like because we have precise match to the CFT, and we don't need to introduce like any additional atomic contribution, I would like to see that this our result also supports that maybe when you compute entropy, I mean with vacuum subtraction, then the atomic contribution just vanish. Or maybe it's just to say that the atomic entropy is some fake thing. But this is again kind of controversial, so we should have discussions about this in the end. So this is like kind of the list of results. And
sorry, what was PI? You said the thing that
yeah. So PI is like any diffeomorphism. So basically, this is just to say that this it's not like the area plus log rho, this generalized entropy operator. It always commutes with PI. It's like it's actually restricted to the psi itself. It is there.
And PIs make sense perturbatively.
Yeah. You can at this point.
Right?
Yeah, at this point, I mean, we treat everything perturbatively. So the PI, you can think of them as perturbative having like expansion to say perturbatively order to G Newton. Questions? Okay, so then like maybe just start from the concrete prescription. So I would just call this like the fluctuating surface prescription. This is the more like concrete one I was mentioning, and you will see why I call it this name. Maybe we have a better name for this, but for now let's just use this like bad name. So we are trying to compute again the entropy. And in our setup, we have ADS-CFT, so the CFT result can be used as a reference answer. So the CFT entropy can just be defined like unambiguously. So at first, before going into any detail in the bulk side, I just give like some very brief like definition of what you use for the CFT entropy calculation here. So you can have, say, bulk graviton states should be due to the boundary stress tensor excited state. So in the CFT, well, we just take a bunch of stress tensor, excite your state, and then you can compute what is the density matrix, and you can compute what's the what is the CFT entropy ambiguously. So this is like just a reference answer. And the bulk side is the the part we need to be very careful about. And so again, as we were saying, we are trying to compute graviton entropies. So if you want to compute their entropy, at first you need to give like some kind of quantization. So we choose this kind of a canonical way of doing the quantization. We define just we treat the gravitons as like mass spin 2 field, have a canonical quantization, and so the any graviton state psi can be defined as there should be a creation operator. Creation operator with some quantum number q acts on the vacuum state. So this is just how you would ordinarily construct the Fock space, and we treat that as our graviton Hilbert space. And this is how you would define your state and your Hilbert space, of course. And on the other hand, you also need to define like what is the metric as an operator. Because now, we have fluctuating metric. We want them to act on the graviton states mentioned before. Then this metric should be now promoted to be operator. So the metric G, we have an expansion of this capital G to be the background, and we have the first order in the expansion, kappa times H. Kappa here is square root G Newton. This part it contains the graviton creation annihilation operator, and we also have the expansion to higher order. I will mention how to deal with these higher order things in a second. But truncate to here, to the linear order, that is just to have a free field for a massless spin 2 field, and having this to be its field operator. Okay, so that is for this part. How do we define the metric as an operator? At least the linear order. So there's one thing I think kind of important in this part of the proposal. It is that we also need to treat the surface, because when you want to compute the area, you also always need to know where the surface is. We also treat the surface as not just like a C number in this Hilbert space. We also treat the surface itself as an operator. So then, if you write down the expansion of the surface, well, you will start from an unperturbed extremal surface. We will call it gamma 0. But starting from the next order, we will have this gamma to be an operator. It is now a linear combination of a bunch of graviton creation operators. And importantly, we need to determine what is this coefficient here for this linear order operator. And what turns out to giving us a working result is that we need to make sure that this gamma 1 as a perturbation, it is always extremal in the corresponding gravitational mode. To be more precise, we know that if we have the background metric and we have the unperturbed extremal surface, the extrinsic curvature for the extremal surface is 0. And now what we require is that now if you turn on the fluctuation of the background, so now your metric becomes G plus kappa H. HQ is just a specific mode. Then you take also the corresponding mode for gamma. You say that now I fluctuate my surface away from the original gamma 0 to this now gamma 0 plus this kappa gamma 1. Then this this extrinsic curvature, it is still 0, saying that this gamma 1 is still extremal in this UN perturbed metric. This is kind of the key part of this definition of this prescription. That's why I was saying it's called the fluctuating surface prescription. Up to now, questions like this maintain extremality condition?
I'm confused about, so you talk about a bunch of operator stuff and then you wrote the k equals 0 condition. That's also, that's a scalar? Or that's a,
Yeah, so here you can just think of it as either as a expectation value equation, or you can just say that I take a particular mode here as HQ, and I take the corresponding mode here, there should be a Q here, as gamma 1Q, and for each of the mode, this thing is
so you mean just the classical equation for k, subject those modes, that's how you pick gamma 1, gamma q.
Yeah,
This is just a linear order, so it's a linear equation, so there's no ordering ambiguities or anything. It just says that gamma 1 is some linear combination of function of h, and then you just promote that to an operator equation.
yeah.
As well, it's very important for you that you always work with a true extremal surface. So as you add the gravitons, you will resolve for.
Yes.
Yeah.
Yes.
Well, in a sense, it's not clear what the definition of that is, right? And this is a definition, right?
The definition.
There are many settings where you can sort of work, where you have a choice, right, between just treating the gravitons like other matter on a fixed background to to linear order, or shoving them in with the gravity side. It sounds like it's very important for you that you just solve honestly.
Yeah.
Yeah.
That's gamma 1 depends on state.
So you can treat as Jeff was saying, if you think this equation is a little bit not specific enough, you can say that both of these are operators and take the expectation value to in a specific state. That will just take out on the gravity side a specific wave function h. On the surface side, it will also just take out this specific coefficient for one mode. And the point is that this gamma 1 in the specific mode should solve the extremal surface condition for if you have the metric for this corresponding mode, metric perturbation for this corresponding mode.
Okay, but that doesn't depend on relation between gamma 1 and h.
Mm-hmm.
Depends on the state to some degree.
At this point, no. We would say that if we have pure gravity, then this map is purely like a geometrical map. If you have matter, and that I think this map from here to here depend on your metric state.
So, are these AQs they act globally? Sorry, which one is the one? HQ acts is everywhere.
That's also an important point. So when we do the quantization, I think at least for me the most convenient way would be that you just do the definition of creation operator or annihilation operator in the global coordinate, not to separate to left and right range or back at the moment. And then when you actually try to say compute entropy or moderate Hamiltonian, whatever, then you do the Berkeley transformation and go to the specific left and right direction. I would say that you want the mode to be smoothly defined across the extremal surface.
Implicitly, we've fixed to some gauge here so that we only have physical degrees of freedom left. Otherwise, H hat would not entirely be determined by creation relation theories.
Mm-hmm.
It doesn't matter what gauge we fix to, we just assume here we fix to some gauge and say, yeah.
Yeah, thanks for the comment. I mean, it is just like to quantize gauge field. Yeah, and to first, I mean, for us to first fix a gauge. Okay. Anyways, so this is I think one of the most important part. And then like if you want to try to compute the any quantities to the order g Newton to 0 we are interested in, there's another thing that you need to deal with, which is like the back direction of the graviton. So we basically require that like this operator g hat acts on the state, always give you an on-shelf state, meaning that it satisfies Einstein's equation. To be more specific here, it is that if you now consider only the metric g plus kappa h, then it only solves Einstein's equation to the linear order, but we want the metric to be always on-shelf. Then you need to add a second order back direction from this HQ that should be quadratic in your creation and operator, and this G2 is specifically defined so that your Einstein's equation now is satisfied to higher order. So in principle, this process should be able to be extended at least morally to higher orders. You always say that, okay, I solve Einstein's equation to certain order, I resolve the extremal surface at this order, and then go to the next order, just going on and until the order you need is reached. So now in this talk we only have the cutoff here. Okay, so this is how we treat the metric as an operator. And for the area, I mean, having all this g and gamma as an operator, it is to make the area as an operator. So area is a functional of your metric and your surface. So now if you have your metric and surface to be both having perturbative expansion, then it's natural to also just do the perturbative expansion for area, and then you will see that now we have a bunch of linear operator, quadratic operator. These are perfectly well-defined operators in perturbative field theory, and we can easily use these to compute expectancy values. And this is what we actually need for this area operator. Just as a remark here, as Raphael already mentioned a little bit, so we always kind of resolve the extremal surface. So in this sense, this area operator has a unique definition. So it's always the area, no matter to what order, it's always the area to the extremal of the extremal surface of the extremal surface up to this order. So then you can check that this result, it is indeed a gauge invariant object, in the sense that first area itself is ecomorphism UR, and second we have a specific definition for what surface to compute area. If none of the things are ambiguous, then the area operator itself should not be ambiguous. So this is the area operator part. I think we kind of successfully make that to be the unique gauge invariant one. And there's also one thing I should maybe mention a little bit, because this is going to be very important in the later discussion, that there is some gauge conditions, because here we need to resolve this gamma 1q. It is sometimes making you feel like it's a little bit annoying, but there is some specific gauge in this gauge that you just don't need to resolve this. This is some condition, gauge condition H. Under this specific gauge condition, the extremal surface, it just doesn't change its coordinate location. So gamma is just gamma 0 by itself, but this will make H to be very specific. You cannot use arbitrary gauge to do this, but you can always find a gauge transformation, starting from arbitrary gauge, find a gauge transformation to make your H satisfy the condition that the corresponding extremal surface doesn't move, its coordinate location doesn't move. We call this the extremal gauge, and it's going to buy us a lot of things in the future. So now, like, let me just first mention that. Okay, so any questions up to now?
Doug, how do you know the operator ordering for the kappa?
Yeah, that's a very good point. So first, yeah, maybe just as like a cheating simple answer, because we are considering vacuum subtracted entropy. So whenever we have vacuum subtraction, all these like C numbers, they're not important. So we just cheat a little bit to say, okay, everything here is normal order. Then it doesn't affect your like vacuum subtraction. But in general, I would think that this like normal ordering, it wouldn't be, yeah. So yeah, I would say that it doesn't really matter when you compute vacuum subtraction to even higher orders. Basically, just because of the same reason I was saying that all these C numbers from commutator, I would just give you, like, get you subtracted if you subtract off the vacuum. Okay, so
Equivalence statement is it true? Vacuum subtraction and normal ordering.
yeah, I mean, I would say that at least to the order we have been working in, yes. If you go to higher orders, I think it should still be true.
Stuff here that wouldn't be true at higher orders.
Would not be true.
Would not be true. Yeah, I mean, like normal ordering will change V by more than a C number if you get above quadratic order. I guess the other comment in response to Ahmed's question is, like, if you want this thing to be Hermitian, then I think at quadratic order it's unambiguous. It's not the same as normal ordering, but so you just have to take an anti-commutator of H and gamma 1, because otherwise it won't be Hermitian, and everything else is just an operator squared, so that's not ambiguous. Higher orders, then that's also sufficient.
Okay. Yeah, thanks for the comment. Okay, so this is the area operator part, and we also need the bulk entropy part. So naively, I mean, what we can do is just as like everyone would do for ordinary matter. So we have this like graph state. We take a partial choice to the complement region, the bulk region, and then we define area. We define this density matrix and define the fundamental entropy to be just rho log rho. But there is some subtleties here. First, I think what I want to mention is that what is your subregion? So I would say that the subregion here, it should be bounded between your like boundary subregion and the extremal surface. But now the extremal surface should be the ones that get fluctuated. This is like one point, that your subregion should always be between the after perturbation extremal surface and boundary subregion. And the other thing, like maybe some experts in the audience would notice, is that this process of taking the partial trace, it depends on like the Hilbert space is separable. But now, if you have gravity, it is a gauge field. The Hilbert space in general is not separable. This is indeed a very, very good question, and I wouldn't go into much of the detail here, but I'm just trying to mention that the condition we imposed before, like here, this condition, in some sense, it is sort of like some PMC boundary condition in Maxwell, in the sense that it takes you out one of the super selection sector, and if you only have one super selection sector, then it's totally safe to do the separation of the Hilbert space. But I would be happy to have more discussion on this, like a little bit later. But up to now, like we pretend things are safe.
What is PMC?
Yeah, perfect magnetic conductor boundary condition. It is to say in Maxwell on the entanglement surface you have zero flux. Yeah, because here like extrinsic curvature is sort of like the conjugate momentum, and we require that to be zero. It's kind of like you require the gauge field, field strength to be zero in Maxwell.
Sorry, and why was it the case in Maxwell that with these boundary conditions, the edge modes that it contribute?
Yeah, so that thing I think I will comment in the very end, but so in the Maxwell, if you really want to, carefully take care of the edge modes, so it is not like a PMC boundary condition wouldn't be sufficient. So the PMC boundary condition I am talking about here, it is literally to say that I have zero flux on the horizon. But what you should do, or say a safer way to do, is that you have to integrate over the profile of flux on the horizon. Then that will possibly give you an actual contribution. But just it's like based on some previous work we had, that thing in the end doesn't contribute to the vacuum subtracted entropy. And so here, like we are saying that we have this condition, it's sort of analog to F is zero. Then this is why I'm saying that it's like taking one super selection sector instead of integrating over super selection sectors. The analog of integrating super selection sector in this case, I would say that it's here like you make it to be some number and you need to integrate over that number.
Have you guys checked that?
No, we haven't. Yeah, no, we haven't. Yeah. But
We checked by computing the bulk and the boundary and seeing that they match with no contribution from it.
yeah.
Wait, wasn't that the goal?
Yeah, I mean, like there should be some more abstract arguments of saying like these animals just never contribute. I mean, I think I've now rewatched back up that these things are fake. So yeah, we have more discussions on this like in the end. This is indeed a very important point. Sorry.
Like another thing in electromagnetism is to fix classical electromagnetic field. And you're talking only about.
Yeah. So like that's the other boundary condition. This is the PMC. There's also the PEC, perfect electric. Just to fix like field and conjugate momentum. Here we're more like fixing the conjugate momentum, but you can definitely try to do the fixing the field itself.
Yeah, but that's like fixing classical background.
Sorry. You're saying that not on the entanglement surface, but like the whole.
Yeah. So then of course no edge.
Okay. Yeah. So.
That sounds like more analogous, but maybe too naive.
Maybe let me try to think about it later. I mean, I heard about this, but I haven't thought like if you can easily just to say that there shouldn't be actual contribution without any like actual calculation. So yeah, maybe let me think about that later.
Well, you're fixing that, so you really fix the background.
Yeah, I mean, like to actually like compute the animals, it's not like actually fixing flux to be some number. You need to fix it to be the number that you integrate over. So that is what characterizes these super selection sectors, and it is like these super selection sectors giving you the contribution. So in whatever gauge you try to fix, I just need myself to be also convinced that there is nothing like this flux to be integrated over that could potentially give you something like the atom. That I'm not so sure about the background gauge you are talking about, so that's why I need to think. Okay, yeah, so, okay, any questions up to now? Okay, yeah, so this is like the prescription part, and now we need to get our hands a little bit dirty and actually do some computation. So the first computation I would, or just the first thing I would mention is just to briefly mention the CFT computation. I wouldn't go into much of the detail, but there is some interesting feature that I think I should emphasize a little bit. So to do the CFT computation, well, I mean, we want to compute, what we want to compute, it is the CFT, or say vacuum subtracted CFT entropy for a subregion, and the subregion itself is like very symmetric. It is like a polar cap. And there is this like CHM map to make this computation of the entropy for the like polar cap subregion easy. by mapping this polar cap to be a thermal, the density matrix for the subregion to be the density matrix for to be a thermal density matrix for like a CFT living on this space-time. This is mainly at least a trick for me. So if you were like very good at CFT calculation, in principle you can do it in whatever way. But one thing I want to show from this picture it is that this map actually gave us something like simplifies our calculation. So this is what you would usually do in the setup. In the original RT setup we were talking about. So you have some state, some operator from the create a state from the far past, and then you have also the dual state in the far future, of course, and then on the t=0 slice you compute the entropy, and the size of the polar cap I will call it to be theta naught. And somewhat magically, through the CHM map, this operator in the far past and this operator in the far future, they get mapped on this Euclidean time circle to be very close to each other, that the separation here is 2 times the angle here. So now if we work in the limit of this angle is small, then you can see that there are 2 operators in this space very close to each other, and then you can use all kinds of OPE trick you have in CFT that makes the calculation easy. So this is more like a technical point, but I want to raise it because first we need to mention the theta naught expansion in the future, and also that maybe this map is useful for some of your competitions. So yeah. Anyways, so this is like a trick to compute the CFT entropy. And just go back to the quantities we actually want to compute. We want to compute the CFT modular Hamiltonian, and in the CFT modular Hamiltonian, we know that, in this at least very simple setup, the CFT modular Hamiltonian can be written as a stress tensor integral. And we have some excited states. We have the stress tensor integral here to represent the modular Hamiltonian. We just need the 3-point function CFT. So that's a very good quantity to compute in CFT. And on the other hand, if you want to compute relative entropy, well, what you can do is that you expand in terms of this delta rho. This delta rho is the difference between the vacuum and the excited state density matrix. And doing the expansion will also make the computation a little bit easier. So I wouldn't go into much into detail here, just to mention that first, this delta rho is controlled by the small parameter theta naught. So then this expansion is actually a valid expansion. And second, when you do any computation, you will basically compute delta rho to the power n the moment. And then you just have a bunch of stress tensor correlator in CFT, we know how to compute these. Then thanks to the theta naught expansion, we can compute the relative entropy. So yeah, this is what we need to do on the CFT side. And any questions? Yeah. So as for some results, well, we have the explicit result for a single graviton state. We have delta k, we have as relative as a theta naught expansion. But maybe one thing I want to emphasize a little bit is that we found it, at least at the beginning, a little bit surprising that you can have a rather large entropy for a superposition state. So here I have explicitly listed the power of C in all this result. So the modular Hamiltonian change and relative entropy, they are both of the order C to the power 0. C is basically 1 over G Newton. And so they are both of order 1, or say order G Newton to the power 0. But it's not hard to cook up a state which has a large entropy. So we can do the superposition for a state which is the vacuum and one normalized excited state. And when you try to compute its delta k, it's not, you're going to find that this change of modular Hamiltonian is an order square root of C, or say it's an order 1 over square root G Newton. This is a rather large entanglement, and we will see that in 5 minutes this match some bulk calculation. But at this point, just from the CFT side, it is, at least for me, very interesting that you have such a simple state. But I mean, and both of them have like order 1 entropy. But you have a superposition, very simple. Then in the end, you get a large entanglement entropy. So yeah, what's the physical meaning for this?
There's no analog of this for ordinary excitations, like for non-graviton, just ordinary particle excitation.
Yeah, I think so. Yeah. Yeah, so maybe this reflects some mysterious nature for the gravitons, but I don't yet have a very good physical explanation. It's just like an interesting fact we noticed.
I mean, mathematically, it's just about the stress tensor PE, right?
Yeah.
But in the bulk, it's like, is it related to the fact that they sort of...
I think Guanda's going to get to that. So.
Yeah, I'm going to recover this from the bulk calculation. It's just like probably I'm not sure like from that specific bulk calculation, although we match it to CFT, that just from the matching, like how much we can say that what's the specialty of gravity from. Yeah, I mean mathematically yes, like the series expansion is for symmetric, it starts with square root g. It's not like for ordinary matter it starts from g, but more deeply I'm not sure. Okay. Yeah, so this is like the boundary part. It shouldn't be ambiguous, just providing us a reference answer. And the bulk part is going to be a little bit technical. This could be the most technical part of the talk, but I'm trying to just at least convey some of the basic logic here. So the first part I'm trying to address, it is this moderate Hamiltonian, the boundary moderate Hamiltonian equals to bulk moderate Hamiltonian. This is a quantum statement. It should be viewed as the expectation value of some quantum operators. So what we're going to do is that we want to justify this quantum expectation value formula by looking at some classical phase space identity. And we can show that just by classical phase space derivation, there are some equations like this, and we can show that this maps to the quantum operator expectation value. Then at a classical value, if this is true, then at a quantum level, this should also be true. Oh, this is the logic. Yeah, so there are a bunch of new notations here. You might feel a little bit bothersome, but just to mention that here, this Q, it is the diffeomorphism charge. So if you're familiar with this famous Ball paper, black hole entropy is also charge, that's exactly the charge there. But if not, it's just to say that gravity is a theory with diffeomorphism as a symmetry. Then this symmetry should have a charge, and this is the charge. And this omega here is the syntactic form. This is not very different from just the inner product you do for just ordinary QFT. In ordinary QFT, you still need to define, say, triangle inner product. And here we have this omega to play the same role. And another thing is that I use this L, C. L is the lead derivative, C is the King vector. So this guy is just the boost generator. So when you look at this quantity, just physically to understand it, so we have a wave function, and you act it with the boost. It is, if you do it in reader, it is just like a time translation. Then this will act as a Hamiltonian, and then you have this Hamiltonian act on H and take the inner product. This is just to kind of give you the energy of the state. So just if you're not familiar with the notation, it is just to say that this is the diffeomorphism charge. This is sort of something like boost energy. Okay, so then with these concepts, we can try to do the match. So we actually do the match of the classical and quantum formula, and the classical one is from the current phase space. The classical and quantum formula, by looking at the specific extremal gauge, we find that in the extremal gauge, this is the easiest to map between one another. But this shouldn't be limited to the extremal case. We will make things easier in a second. But let's start from the extremal gauge. So we have 3 terms in both of the formulas. So first, let's look at, for example, this term. This term is supposed to correspond to the area, and this is not a very hard computation, but you can check that if you are in the extremal gauge, this Q, after doing the calculation, evaluated on the extremal surface, it is itself just the area. So then a change of the charge and a change of the area apparently have to be the same. But this condition, it requires the extremal gauge. So this is one mark here. But anyways, I think it's extremal gauge. This map is easy. And the other point, it is about the inner product, or say we call it canonical energy as a more technical term. This thing should be matched to the change of bulk modular Hamiltonian. So I want to talk about the map from here to here. And then what we need to do, well, it's actually also a rather straightforward calculation. It turns out that if you do calculation in the extremal gauge, it is easy to introduce some kind of linear basis to expand your extremal gauge wave function, and then by just a simple linear calculation, you will see that the result takes this form. So this is integral of the energy. Omega is the linear energy. I should mention this a little bit. This beta here, it is the Berkeley coefficient. You can view it as the expansion coefficient if you have a global mode and expand it on a basis of linear modes. That will give you this Berkeley coefficient. So this is purely just change of basis. But on the other hand, if you try to evaluate the bulk modular Hamiltonian change, you will see that the modular Hamiltonian in the bulk in linear, it should be easily written as sum over omega b dash b. That's rather standard. But you have these two states. These two states are the states defined in the global coordinate. Back to Orban's comment half an hour ago. Then you have a global state, you have a linear state, you take the inner product. That will also give you some and it turns out that the quantum expectation value calculation exactly match the current phase space quantity, which we call canonical. It is not very surprising, but I would like to mention that there is some subtleties, and the extremal gauge condition here is important in the first important. So this is so the canonical energy part, and in the end we have the boundary part. So the boundary part is is much easier because on the boundary the scaling vector approaches to a time-like scaling vector on the boundary. So this is the boost charge asymptotic on the asymptotic boundary from the classical point of view. But on the other hand, in the quantum theory, the CFT, you can also define your boost charge, and that's going to just give you this CFT modular Hamiltonian. So there's no surprise that these two match. So then, every term of the classical and quantum equation matches, and we can prove from the classical phase space that the classical equation is true, that the quantum equation, at least its expectation value, should be expected to be true. So this is the most technical part, I guess. Any questions? Okay. So then just to briefly mention about the gauge invariance. So we can also make everything to be gauge invariant. In our previous definition of the quantum operators like area operators or bulk entropy, that operator is defined at least seemingly to be gauge invariant. And we can also make the classical equation to be gauge invariant. And we have two gauge invariant equations, and they match in one gauge, they should match in arbitrary gauge. So that's basically finish the proof, gauge invariant version, the proof that the bulk and the boundary modular Hamiltonian should match. So this is some rather abstract arguments using a lot of these phase-space technique. We can also give an explicit check. So we indeed have some states For example, there's a single graviton state, and there's also superposition state, and we just explicitly tested that for both of the states, the first equation is true. So then, like, it's more than just an argument. We indeed have some evidence, concrete evidence that this is true. Maybe some more technical point. So for the single graviton state, what we try to compute is moderate Hamiltonian or average change. It starts from order kappa is square root G Newton, so order kappa to 0 is order G Newton to 0. This is not that surprising. This is kind of like ordinary matter. But this guy here is again like kind of surprising. So we have one single graviton state having superposition with a vacuum state. And for this very simple superposition state, when we try to compute its expectation value of the area operator, you will see that at the order like 1 over square root G Newton, there is a non-zero matrix element. So just to make it a little bit more clear, so we have our area operator to be the vacuum value plus the first order expansion is square root G and a linear H this is the only term you have in this linear in square root G order, and we have G Newton order among the other things. Now we just focus on this part, and we promote things to be operator, and this is just like the first order derivative of the area with respect to the metric times the graviton operator H, and then this guy, if you put it into the expectation value, then when compute the superposition state, there will be a term like 0 H single graviton state. This guy has one of the equation operators, this guy has one of the ionization operator, and these two just contract with each other and give you a non-zero result. So this is the analog result of the CFT large entropy, because the area from contribution from here is of order square root G. And you divide everything with 1 over 4G. If you want to find its contribution to the entropy, then this is large. This is 1 over square root G, matching the previous square root CT. So this is not just like an order matching. We also match exactly like the function. So we think that the bulk and the boundary is indeed giving you the same result. We are using the correct statement, the correct prescription. But as I was saying for a few, this is more or less like a mathematical fact in the sense that the graviton starts from the square root G, while your matter starts from G. So then what is the more profound understanding physically? I'm not exactly sure.
Yeah, this is what I thought, and by the way, when you first set the result, and because you put the single graviton, you will change the geometry. And the area is operator.
Yeah.
So now, of course, this surface is grooved because 0 and G has a different area.
Yeah.
And then cutoff is a G Newton or a delta. And the entanglement is you really have to sum up all these things. Okay, that's why area over G Newton. So that will add up. If the geometry slightly changes, and then the entire effect over the surface will keep happening. So what I think as analogy in QED is probably wrong, because then QED photon excitation will back react to the electromagnetic field, but gravity will back react to geometry. So it's something like not photon, it's just you have to put the electron.
So if you have max field,
what do you do?
It changes, electromagnetic changes. So what I said is obviously wrong, right? So not fix the electromagnetic field. If you're doing this kind of thing, superposition of 0 electron plus 1 electron, and of course electromagnetic field is slightly different.
Sorry, single photon.
Not photon.
Okay.
I saw the photon, but photon is neutral. But electron is charged, graviton is charged.
I don't think this is about the self-interaction of the graviton. This is just that there's this area operator in
Yeah.
generalized entropy, and it's just a linear. It's
And-
not even like back reaction of the graviton, right? It's just the graviton itself is perturbative change in the geometry. Like even if like this at this order the graviton is totally free, so it's not the back reaction of the graviton
It's
on the
not.
geometry. It's just literally it's the fact that there's this explicit A over 4G term, and like H is itself changing A.
But then what's the kind of physical interaction if nothing is happening near the boundary?
There's no interaction as such. It's just that you've like changed the geometry. It's like
But you said it doesn't change.
it's well it changes the geometry just because gravitons are excitations in the geometry. What I'm saying is it has nothing to do with GR being nonlinear. It's linear order.
Oh yeah. That's
So it's not like yeah. So maybe I misunderstood what you were.
I think what I said is that physically this reflect the fact that this single graviton will change.
Yeah.
Geometry.
Yeah.
And then that this is the entire surface is just the whole effect is like it's enhanced by one word that type of scale for area. So and then I just said that my analogy with the photon is totally wrong. The analogy must be electron. So this position stays.
Yeah, I don't think it's about the graviton being charged under self-charged, because like if the formula, if generalized entropy say had a contribution from the electric field on the surface, like a classical contribution from the electric field, then you would probably get some large correction from that, but it doesn't, right? It's the fact that generalized entropy is entropy plus A over 4G, and that A over 4G term is explicitly what the graviton is the fluctuation.
Isn't that the same kind of H
No, it's not.
I don't think so.
Well, it's the effect of it's the expectation value at the edge, but it's like it's not an edge mode contribution to the entropy. Like the log rho term doesn't have any contribution to the edge. It's just the area term that gets a contribution. I mean, classically it'll come the A over 4G is at the edge, right?
It doesn't look the same if you treat it this way. But isn't that possible that it's kind of related? I don't know. No, it's just simply.
I mean, people have tried to argue that the A over 4G comes from an edge mode term. So
yeah, but that's not a. I think that's more of an analogy than a precise statement. I mean, there's this sort of under RG flow, then it's the closest statement I would know.
But it's definitely not clear this why it should be net mode at all.
Yeah, I mean, I want to say this is why I'm more involved here. Yeah, okay. So this is like the most technical part, and now we have just a little bit of results to introduce, and then we can get to the more exciting proposal. So we computed basically previously the moderate Hamiltonian, and we all know that if we want to get the entropy to match, we still need to match the relative entropy. And to do the relative entropy calculation, now we really don't have any classical phase space thing to help you, or at least I don't know of. And then you really need to actually compute what is the relative entropy from the bulk. This is not that much different from the boundary calculation. You just still do some moments of change of density matrix. There is some technical detail here, but I think I'm going to skip it because of the time. But in the end, I just want to say that we indeed get a match for the single graviton state, that the bulk relative entropy matches the boundary relative entropy. So, up to a certain order of theta naught. So then, this is also a process match, and we can say that the generalized entropy formula we wrote down before, it got tested for the states we have been considering fully. So yeah, so this is the end of the more technical part of the result. Any questions up to now? Okay. So now, I think I'm going to spend some time on this, hopefully all the proposal. So previously, as I was mentioning, so that the previous prescription is more like, it is a fluctuating surface prescription. So the above approach, as I was saying here, it is like a sort of like extremizing over surfaces. I say, okay, in principle you can do it to higher orders, but for me is that it's not really clear that how to do this to higher orders, or maybe more subtle for me would be that how to do it with matter. Is the extremal, but when you extremize the surface, what to actually extremize over to higher orders is not super clear to me. Is that just
I guess
that?
one comment is that in what we said about extremizing, which is extremizing area, right? But if we're doing QES and we want to go to higher orders, then we need to extremize entropy in some manner. It becomes kind of unclear how to do that.
Yeah, this is what I was mentioning. Like you just extremize over, the geometrical quantity, or you also take into account the matter part. If you want to go to higher orders, they do matter because now the matter entropy can compete with the geometrical part.
Sorry, when you say higher order, you mean higher in H?
We're saying G Newton because H is always square root G Newton, so you have a lot of H's. It's like higher order in G Newton.
Is it difficulty that at higher order you have to include back reaction of the gravity of the geometry?
I would say that for me the most mysterious thing is that how to have the interplay between the graviton state and the matter state. Like now their contribution to the entropy can be at the same order, and what you actually extremize over is not super clear to me.
But you expect that the non-linear nature of GR is still surprised?
Here we already need some non-linear nature of GR, right? So when I was saying, not here, where is it? Here we already need the non-linear nature of GR, like the gravitons themselves, the free gravitons can have back reactions to geometry. This is because of the non-linear relative GR. So this is not particularly about non-linear relative GR itself. I would say it's more like having matter together.
I guess I was referring to the self-interaction.
So the back reaction not being classical. Here we have G hat 2, but we're only dealing with stuff linear in it, so we can sort of treat it as a classical expectation value.
Right.
Once it starts getting quantum mechanical and also the entropy terms competing with the area, then you end up in
So this thing you said about self-interactions is taken into account by the back reaction. You can prove that including an interaction for the graviton with an H cube term would be equivalent to doing this back reaction.
Oh,
So we proved that in the paper.
Okay. Thanks for the comment. Where was I? So I was saying, it's not very clear to me how that can be done to high orders. So there should be some alternative prescription. So the alternative prescription would be to start from the observation that at least at linear order, the order of gamma 1 we have been talking about, the surface perturbation and the classical diffeomorphism, they're equivalent. So whenever you have a surface perturbation, your external surface is kind of fluctuated away, you can always do a quantum transformation and put it back. So then instead of extremizing over surfaces, we might want to extremize over diffeomorphisms. This is a little bit, weird. But on the other hand, if you try to understand diffeomorphisms as, gauge invariant, as gauge equivalent quantum states, then it becomes a little bit, more physical. It is to say that I now try to extremize among the states that are gauge equivalent. And hopefully, this concept will in the end lead us to the all order prescription, because these states should be able to get defined to all orders in perturbation theory. So before going into the proposal, maybe I'll give some remark. So first, I was saying just to compare. The previous prescription is that I have a fluctuating surface. I don't really require a specific gauge. And the new prescription would be that I'm going to highlight a specific gauge, or in other words, like a specific element among all the states that are gauge equivalent. And the condition is that the surface stays unmoved. And the second remark would be that there is like different notion of gauge equivalence. So classically, a gauge equivalence, I mean, for gravity, the gauge equivalence would be that you just have the diffeomorphism inverse. You have a state, you change the coordinate, it's still the same state. But at a quantum level, like we want to have some, stronger gauge equivalence, especially when you now try to like also take into account for matter. So classically, it would be that P is the diffeomorphism, so this is just an infinitesimal coordinate change. That should not be ambiguous. But here, for like the quantum one, we want to say that the state psi is gauge equivalent to any state. Like phi can be arbitrary, P act on phi plus psi itself. So the more important thing is that like the object you act on with diffeomorphism is not necessarily psi itself. So this is like more, it's a larger set of like equivalence relation, and because if you want to do things in quantum at the quantum level, incorporating matter at the same time, this should be the symmetry you have in your formula. Just to understand this a little bit better, you can think about, say, now I have a superposition states with, for example, one matter profile, and we have some graviton like excitation on top of that. The other matter profile, some graviton excitation on top of that, and then take the superposition. Then, like, if you now do diffeomorphism, the like diffeomorphism for the two states can be different, like the fluctuating of the fluctuation of the surface corresponding to one matter state can be different from the fluctuation of the surface corresponding to any other matter state. So this is like to explain why we need this like larger set of equivalence relation. So then what is the proposal? The proposal is that we still write down the generalized entropy in terms of this like familiar QES form. There is something like we want to like improve that a little bit. So first is we want to introduce this like group averaging inner product. This is if you were familiar with say the work by say Morrow for others, that's exactly what it would be. But if you're not, I'm just saying that like the group averaging would be that the inner product psi 1, psi 2, like this group average one. Maybe I'm going to use this to be the group averaging for a second. This is defined to be integral of dg and psi 1, g, psi 2. And you can see that this, by definition, like this inner product is manifestly gauge invariant. So this is like the first like kind of improvement we have to make the inner product to be manifestly gauge invariant. And more importantly, we need to like specify what is the state here. So the state here it satisfies the so-called quantum extremal gauge condition as I was mentioning. So the commutator between this like entropy operator, like A over 4G minus log rho, commute with any diffeomorphism and constant itself should get you 0. So if you have a psi satisfying this condition, then you can use this to compute the generalized entropy. So why this is relevant? Why this is related to what we were doing? This is related to what we were doing because if you just restrict to the order we have been working with, this psi here, I mean it's not. It shouldn't be understood very abstractly, but you can just view it as choosing the gauge of extremal gauge in the previous case. So previously we were saying that the extremal gauge is the gauge in which the extremal surface is not fluctuated away, and here this is more like the quantum version of that statement, but made it to be this more gauge invariant condition. And maybe just to mention one thing, that in the area operator, we only use the unperturbed surface, not perturbed surface. Okay, but anyways, so this new proposal is to use a more manifestly ignorant way to define your states, to define the inner product. That on the right hand side, what we have here should be manifestly ignorant. And out to the order we have been working with, this condition reduces to the condition of the state side is in the extremal gauge, because in the order we have been working with, this term cannot compete with this term, so just throw it away. And P and A, commutator, that is just to say that it's a diffeomorphism. And sorry, it's not a diffeomorphism. It's like partial A, partial gamma. Gamma is the location of the surface. So if the surface stays extremal, then this commutator can be 0. So yeah, in any case, this is like the all-order improvement to the previous extremal gauge, and we hope that this proposal can give us the all-order definition of the generalized entropy. But it would be a little bit hard to check it. But I'm happy to discuss with any one of you, if you have any comments or suggestions of how we should understand this. And yeah, anyways, so in the end, what we have is this is like a discussion. So we have a bunch of results. The first three, they're the more concrete ones, and I put the big smile here because we're sure, 99% sure they're true. And in the end, I also introduced this group averaging, this all-order proposal hopefully can give us generalized entropy for even including gravitons to all-order in G Newton, and we hope that's also making sense. And in the future, there are a bunch of things that's definitely interesting to do. First is to do QES, because now we are basically dealing with the very classic RT setup. It is still the classical extremal surface. Now, if you do include matter, and there should be a way to having rather large amount of matter field, so that the matter entropy can compete with the area term, and we need to try to find that in that case whether our proposal works or not. This is what I mean by the QES, because now we don't have matter at all. So yeah, and we also try to do say high relative gravity, high order fractions, or maybe black hole background. But I'm not personally very optimistic about whether these things can be explicitly done. But yeah, that's something to think about. And some other important thing would be that to think about the path integral derivation and maybe some algebraic description. I think path integral one would be kind of doable. But yeah, in any case, just to summarize, we provide a prescription of compute the generalized entropy including graviton contribution, and hopefully this there is a proposal that works to all perturbative order, but we do have very concrete results to order G Newton to 0 that our prescription works perfectly. So yeah, okay. Yeah, questions?
The quantum extremal gauge thing you mentioned is kind of like a QES prescription, right?
Sorry, say it again.
The quantum extremal gauge, yeah, the quantum gauge that you mentioned at the end is kind of like a QES prescription.
Well, so this is the improvement of QES prescription if you want to have gravitons. And the point is that because gravity itself is a gauge series, we have a huge amount of gauge redundancy. It is to take a particular one in the gauge orbit, that is the one satisfying in the extremal gauge condition. Use that to try to compute the, try to take the expansion value to get QES. Yeah.
I'm still trying to get the intuition right for the square root of G enhancement for the change of the area. If I go from your ordinary RT surface to the setting with a black hole, I consider a state where I throw a graviton into the black hole. So it has to be sufficiently localized to do that. But if I do that, I can change the area by, I think, order 1, just like for any other particle, right? And then we
If
still
you throw it
extract.
in from one side, then yes.
Yeah.
Like a two-sided.
Yeah, I think for
Like-
two-sided.
Even for a one-sided black hole, they just add a graviton to it, right? I would change the area of, let's say, some
Yeah, I mean, if you
by 1.
well, if you have a one-sided black hole, then the entropy could be 0, right? Like,
No, well, there's this funny calculations on what he did with these islands.
okay, fine. None of this is evaporating, but okay. With a black hole, if you start in like some sort of microcanonical ensemble where the energy is fairly fixed, then a graviton can't change the energy very much, and so this linearized term will just vanish.
I'm trying to understand like what. So it seems pretty obvious that you can't create these sort of superposition states that will then have like a very large change in the entropy that's equivalent to square root d. But what marks like the boundary between a regime where you can do that? I mean, what's happening?
Is there some constraint that like stops it happening? Yeah, I mean, like if you started with the thermal field double state and then you inserted some stress energy tensor, superposition of stress energy tensor and no stress energy tensor in Euclidean time, then I expect you would get something non-zero. Yeah, there's nothing wrong with that. You've done right.
But sorry, but something with a 1 over a square root. Okay.
Oh, you get an order 1 over the square root.
1 over square root.
Yeah. There's nothing that stops that.
I see. Okay.
Yeah, inserting a stress energy tensor is like taking a derivative with respect to beta and then taking a superposition of that.
So is it when I insist that the graviton fully enters the black hole that I'm going to go down to order 1?
Yeah, I mean,
Maybe that's the
it's
local.
well, it's when the graviton is just created on the right hand side. I think then it like can't change it. Like, it's when it's space like separated from the like if you do something unitary that's space like separated, then you can't change the area at all. If you do something non-unitary, it's not actually. So say you just measure the energy of the thermal field double, right? That's something in infinity, like to orders 1 over square root g. That's like a graviton mode effectively. And if you measure it to be higher than average, then or lower than average, that's an order 1 over square root g difference in the area. So these things are pretty common. But if you're in the microcanonical ensemble, you won't get something like that, and it's just the state is a bit odd.
Thanks.
Because Jeff said that's not, so probably, or most likely, or maybe even a higher probability, right, than I know. But suppose you do what I said exactly, this is maybe H mode or something. At least, let me tell you what I kind of felt, like intuitively, and it could be totally wrong somewhere. Suppose you try to change the state at the higher order, let's take a higher order prescription. Suppose you try to change the state by coherently exciting graviton, and usually that will change geometry, but let's not change the geometry, just put the bound A dagger and A dagger to be very high order. And you describe that way. And then of course entanglement, it changed, but in your prescription, change coming from the area term. It's a high order area term and cross term and so on. But you could interpret this as a classically changing geometry, that's why the area changed. So area term changed. In a sense, it's a classical effect. So I thought your prescription is putting this classical effect into all the area term. That's why you don't have extra edge mode because you already kind of absorbed that effect into the area operator thing. That's a specific prescription, specific gauge in such a way that you view all these effects as from area term if you fix the state. And if you fix the base state, And even if classically different geometry, as A data, you can do that, right? And then like coherent excitation. Then all those effects shows up as a hat thing. So in that sense, it's the equivalent thing, like classical, like edge mode type thing, and then your A hat.
Yeah, I mean,
And going back to the single gravitons, that's why I said like maybe this superposition is effectively looking at the brewery or area. It doesn't look in that way in your prescription. It looks as an offline element of a operator, but maybe equivalent if you do it in some other way.
I guess it depends on like what you mean by additional contribution, right? So if you just say that that's some contribution from the extremal surface, then well, pictorially what you said definitely makes sense. But I would say that additional contribution it comes more from like these kind of selection sectors, just to have an analog of to the Maxwell theory, then I still couldn't think about, like what you just said, how that can be related to the Maxwell story.
Oh yes, H mode may be wrong word, like the classical effect of the
yeah, well, that I agree with. I mean, like as
sorry, my wording may have been
yeah, as Pratik was saying, like there is always like some hope that we understand able 4G just to be some script. Yeah. So
H mode may have
that I agree with. Yeah.
Then you see this one over G Newton angles because that's it. So it's a square root G. It's more effective relatively.
Yeah.
Right, in terms of 1 over G.
I'm still trying to understand like why it never appeared. I mean, you were like understanding why it never appeared like this large thing never appeared in say Maxwell or say Young-Mills even.
Yeah, that I don't.
Okay.
Sorry, isn't a separation into edge modes and bulk modes H dependent?
That's a good question. So, I mean, as I was saying, I'm kind of brainwashed by Jeff. Like, Admiral is kind of fake now. Basically, yeah. It makes sense. It's not making sense. It makes sense. Like the edge mode, whenever you do the contribution and see it, appear, it's always like appear in say vacuum entropy, for example, and that's itself not as that like finite, well-defined quantity. And when we look at the way people do the calculation, it's always like introducing some cutoff or lattice, whatever. So is it actually just some like artifact of regulator maybe?
But in just QFT, there's like universal terms that change when you change the edge mode contribution, right? It's not like nothing.
Right, that is true.
Like, and you seem to think in the generalized entropy it doesn't matter.
Look, the edge mode stuff can be thought of. Entropy changes can be broken down into two things, like modular Hamiltonian and relative entropy. Relative entropy is well defined in continuum theory, and so it doesn't involve any bullshit like edge modes. The modular Hamiltonian is just some linear thing, and basically in the continuum theory, what it comes down to is there's some like ambiguity of how you define a one-sided modular Hamiltonian. Right, because only the two-sided modular Hamiltonian is a good operator, and so the one-sided one you can sort of arbitrarily add a boundary term to it. That's like Jimmy edge modes. And then the claim is just in relative entropy, in generalized entropy, the right modular Hamiltonian to use for the gravitons is like the area term, obviously, plus like a term that has no boundary contribution in extreme gauge. That just empirically is what works. That's like a natural description is what works. So, yeah. In the continuum theory, I think that's sort of all you can say, and otherwise entropy stuff is just not defined. In ordinary gauge theories, you can regulate everything on a lattice and say a lot of stuff. I don't know how to regulate gravitons on a lattice. That seems problematic, so it's not clear to me if there's much more to say than that.
Yeah, maybe just to comment on what Jeff said, like here indeed in our construction, you can just put something on the like rectangular surface and make it to be gauge invariant in the sense that you use whatever gauge to evaluate it, it always gives you the same like number. And there is no a priori if you don't do a CFT calculation. You can put it there, like it's fine. But it's just like you do the CFT calculation, you see, it just seems to be excluded by the CFT. I mean, you add that in, you cannot match CFT. You don't add in, you have CFT match.
Probably not explaining anything, but technically, this big enhancement coming from like a divergent piece, right, of the entanglement entropy area over cutoff plan.
The thing I was saying is not necessarily coming from divergent piece, right?
I think that's from the area piece, right? What would be divergent impurity? And then,
yeah,
and then QED, of course, even if you just take that, you know, excited electron or something, surface doesn't change, this condition, nothing changes. And the gravity, of course, partly up to the space-time, so changing this leading piece. So it's, in that sense, it's just gravity. Obviously, background, if you don't change background anything, then this contribution won't be there. So it has nothing to do with the electromagnetic mode or anything like that. Maybe this is H mode for gravity, whatever that is, but it has nothing to do with H mode in that electromagnetic sort of thing, right? It's just simply this lattice, even lattice and then region backreact. And this, in field theory, it's leading divergent piece is source of this. It shouldn't happen in anything other than gravity.
Yeah, I know that. I probably need to think about it.
And then I'm also probably not saying anything.
Yeah, maybe that's.
I think